So today we're going to be talking about the Hilbert transform. I don't know if you read this section. Do you all read this section? Did it make any sense to you? No. How about you, Shane? Did it make sense? Brian, did it make sense?
I didn't get a chance to.
Didn't get a chance to read it. Okay, that's probably good because it actually didn't make any sense to me either. So I went through it and tried to approach it. I think the authors maybe are assuming knowledge that they that as the presentation of the material seemed to be pretty opaque. So I went through everything in a backwards way, and hopefully it will be clear. So maybe for the best, Brian, that you did not. Okay. So so let's start out with part one. Poisson kernel, and Poisson. So let me first put up a couple of useful formulas. So here's an elementary integration formula. First is this for a complex number z with imaginary part greater than 0. The integral from 0 to infinity of e to 2 pi I cz dx equals -1 over 2 pi I z. Okay, so just a formula that will be useful. And then the second one follows from the first. So the proof of this one is just do the calculation and take the limit. So if you do this calculation, if you do this interval, you get 1 over 2 pi I z, e to the 2 pi I, and z equals 1. And then you just take the limit. So it's just a calculation. The second, so that's the first formula. The second formula is this one, the integral of e to the -2 pi modulus c y e to the 2 pi I c x dx equals 1 over pi y over y squared plus x squared. Okay, so let me, just for the heck of it, let me put up the proof. The proof is, again, just a calculation. You take this thing, and you, so this is for, so you break it up into two integrals, right? Where c is positive and where c is negative. Dx plus the integral from 0 to pi e to the -2 pi 2 pi cy e to the 2 pi I cx dx. So, just using the opted value, break it up into two integrals. Right? You recognize this one as e to the 2 pi I c x plus iy dx plus integral from 0 to infinity of 2 pi I c negative x plus iy dx. Right? And then you use the first formula. If I over 2 pi, 1 over x plus y plus 1 over negative x plus y. Right? And that gives you the end. So just a calculation. take your integral, break it up into two parts, and then use the first formula, and we'll put it back together. So these two formulas will be pretty useful in the class. Okay. So I'm gonna erase this. Yeah, so I should say for the visitor that the course is called functional analysis, but it's sort of like functional analysis and applications in harmonic analysis. So this chapter is really harmonic analysis, getting some of the introduction of harmonic analysis. So, okay, so we define these two things. We define the Poisson kernel. P sub yx as y over x, y over pi times x squared plus y squared. So that's this thing called Poisson kernel. And we define the conjugate Poisson kernel by q of y as x over pi x squared plus y squared. And the first thing that we're going to go for is the following proposition called the Poisson integral representation. And it tells you about the convolution of f with the Poisson kernel. Okay. So given xy in the upper half plane, okay, so y is greater than 0, and f an L2 function. Okay, f an L2 function. We're going to say something about the convolution of f against this kernel. And it turns out that in the L2 sense, this equals this integral. Okay. So the way you want to think about this is, if we didn't have this term here, then you recognize it. What is it? The inverse Fourier transform. So this would be the inverse Fourier transform, right, of the Fourier transform. Right. So this is it's basically saying that right. So this would just be the function itself. If you didn't have this term, you would actually recover the function itself. Right. In other words, this sort of tells you that as y tends towards 0, right? As y tends towards 0, then these convolutions maybe recover your function. Okay. Right. As y tends towards 0, the Poisson kernel, and you can actually think about this, right? As y tends towards 0. So anyway, the Poisson kernel becomes more like more like the Dirac delta function, and so you're going to recover your function. Okay. One also has the conjugate Poisson kernel representation, Poisson integral representation. F involved with Qy is this sort of thing. Negative 2 pi I Cy sine of C over I e to the 2 pi I x C C. Okay, so you can think of this as what it says about the Poisson. If you're convolving with the Poisson kernel, what it says is that you take the Fourier transform of your function. You take the Fourier transform of your function, and then you multiply the Fourier transform by this function, right? Multiply the Fourier coefficients by this function, and then you take the inverse Fourier transform of that. Okay, so this is something that one does to create operators. You take a lot of operators are like this. You take some function and then you flip it across into the Fourier transform sign. You multiply it by some function over there, and then you take the inverse Fourier transform. And so these two, you can. What this says is that you can realize these two things to be that sort of operator. Okay. So okay. For the proof of this, let's first assume that f is a short-class function, and we define. The proof will just be by Fubini's theorem. You define this function phi as f of t e to the negative 2 pi ct e to the negative 2 pi modulus of cy e to the 2 pi I cx. And you notice that since when you take the size of this, we just get f of t e to the negative 2 pi cy. It's integrable. Phi is integrable. And we can use Fubini's theorem. So Fubini's theorem says that that we can do this. We can change the order of integration, so that you can get f. So we can integrate with respect to c first, or we can integrate with respect to t first. Okay. And you'll see that basically gives it this. So let me write out the integrals and then we'll talk about it. So I'm just saying that we can use Fubini's theorem. We can change the order of integration. Okay. So what do do you see on the right hand side? What do you see on the right hand side? Right? Well, we're integrating with respect to t, right? So these terms will fall out, right? And these terms will be pulled out. We've got f of t e to the negative 2 pi I ct dt, right? What's that? That's just that's the Fourier transform, right? So you get the integral of Fourier transform at c e to the negative 2 pi cy e to the negative 2 pi I cs dc. Right? And what do you see on the left-hand side when we integrate with respect to c first? Does anyone see it? It's from the first formula. So we have this formula over e to the negative 2 pi cy e to the 2 pi I c cx c equals 1 over pi y over y squared plus x squared. Right? So integrating with respect to c first gives us f of t p sub y x minus g dt. Right? Right? And so that's what we wanted. Right? We get the convolution of f against the Poisson kernel, and then on the right side you get this expression. And then you do something similar. So that gives you the formula for Schwartz class functions. And we want to extend it to L2 functions. So, to extend to functions in L2, so let you sort of do what you would expect. Let f sub n be Schwartz class functions, such that fn goes to f in L2. And then you notice that by Cauchy-Schwartz, if we look at say x minus t times fn x minus t d by t dt, if we look at the difference between the convolutions, right? We look at the difference. We take the difference of the absolute value of the difference of the convolutions. Right. So we look at f involved with p sub I minus f involved with fn involved with p sub I. Right. We see that by Cauchy-Schwartz, we can control that by the L2 norm of this against the L2 norm of the other guy. And so in the limit, this thing goes to 0. Goes to 0 as n goes to infinity. We also see something similar for the other part. If we look at the difference of the integrals of the expressions using the inverse Fourier transform, we take the difference of those guys. Well, if we take we use Cauchy Schwartz on that again, we get f minus fn and the integral of f e to the negative 4 pi c1 c. So again, what happens is that as n goes to infinity, this goes to 0, right? And so that gives us that the formula holds for L2 functions as well. So it may seem that I'm just putting out like formula after formula. I'm sorry, that's true. Right now I'm just going to give you some formulas, and then later on, when we start talking about the Hilbert transform, it'll all come together. So I'm afraid just bear with me for right now. I'm just going to put up a string of formulas. We started off with those integration formulas. Now we've got the Poisson integral representation. Sorry. I tried to make it coherent, but I didn't necessarily try to make it appealing. Okay. So, I didn't think about how to make it more exciting. Okay. So we have now the Poisson integral representation, and we make the following observations. So observe, first off, that maybe the first thing that you observe is that if we take the Fourier transform, so what happens when we take the Fourier transform of the Poisson integral representation? Well, if you're taking the Fourier transform of a convolution, what happens to that? Fourier transform of convolution just becomes a product, right? So, and then on the right hand side, what happens when you take the Fourier transform? Well, this is the inverse Fourier transform of something, right? This thing here, this expression on the right is the inverse Fourier transform of this thing, right? So when you take the Fourier transform of the inverse Fourier transform, you're just going to recover this function here. Okay. So what you get is f hat c times the Fourier transform of the Poisson kernel is going to be f hat c times this thing, right? So in consequence, we know what the Fourier transform of the Poisson kernel is, right? We have some formula for the Fourier transform of the Poisson kernel. It's just this. Okay. And similarly, the formula for the Fourier transform of the conjugate Poisson kernel is just going to be this one. Okay. Second thing you notice is that if you take these two formulas, and multiply the second one by I, and then add them together, what do you get? Well, like what's well, you're just going to get the integral on the right, right? But it's going to be from zero to infinity, right? Because you're multiplying by the sine of c, right? So you're going to get twice the integral from 0 to infinity, right? You lose the negative portion of the integral, right? Okay. So if we divide this thing by 2, right, we see that we have the following expression, that this is equal to the integral from 0 to infinity of fc e to the 2 pi I z c, where z is x plus yi. Because we're going to end up with negative 2 pi cy e to the 2 pi I x c. C is positive. And so you put this together. Okay. Is everyone all right? Okay. Okay. So let me just make some comment about the relation with complex analysis. For f in L2, we define the Cauchy integral so recall, we mentioned this before at the Cauchy integral. We define the Cauchy integral of f on the upper half plane by f of z equals 1 over 2 pi I, the integral from minus infinity to infinity of f of t over t minus z dt. I'm just gonna put down a fact that f of z for z in the upper half plane, f of z actually equals 0 to infinity, actually equals this integral. That we just found. Okay, so there's that's to say that the Cauchy integral can be expressed in terms of the Poisson and conjugate Poisson kernels. So this is the thing that we just it won't be that important in what we're doing, but the proof basically follows. It will. You can basically get the proof following the same proof of the Poisson integral representation. Okay. Sorry. Okay. So now let's get to the Hilbert transform, which is okay. So Okay. So let me just put up the definition of the Hilbert transform. Here we go. For f in L2, we define the Hilbert transform H by h f x is the integral of the Fourier transform of f times the sine over I e to the 2 pi I c x b c c. So this is again, expressed as a what's called a multiplier operator. You see what the Hilbert transform does, right? You take your function and then you flip it over into the Fourier transform side. You multiply the Fourier transform by this factor, right? So basically, you're taking the Fourier transform and then you're multiplying it by the sine, right? So you're preserving the guys over here, you're flipping the guys over here, and there's also this factor of I involved, but you sort of ignore it, right? And then you take the inverse Fourier transform of that. Okay. This is what we saw earlier in the context of. We first actually saw this in the context of a Fourier series, right? You take the Fourier series, you have some function, you take its Fourier series, you multiply the positive, you multiply the Fourier coefficients for right? You multiply the ones for positive n by sine over I, right? And then you go backwards, and that's the Hilbert transform. Okay. So this is the Hilbert transform. It's one of the important operators. It's sort of like the prototypical operator in harmonic analysis. Okay. Well, we're not going to use this right now, but let me also introduce something called the orthogonal projection. So we define an orthogonal projection P on L2 by Pfx equals the integral equals this thing. So c 0 infinity c e to the 2 pi plus c dx. Okay. So you see what this guy does, right? Again, you take your function, you flip it over to the Fourier transform side, and then you preserve only the ones for positive c. Right? You chop off all of the Fourier coefficients for c negative. Okay. And then you flip it backwards. Okay. So this is a projection. This is a projection onto the subspace of functions f, for which f hat is 0 for all c less than 0. Almost there. Okay. So just a couple of observations. First, P equals a half the identity operator plus IH. Right? Right? If you take I times the Fourier transform, right, and then you add the identity operator onto it, well, you're going to get P. Read it twice. obviously. Right. Second observation, H is unitary on L2. Right. Because what's the Fourier transform of H? Well, the Fourier transform of H is it's just going to be this thing, right? It's the Fourier transform of X times this constant, but this constant has norm 1, right? So the L2 norm of the Fourier transform of H, L2 norm of the L2 norm of the Hilbert transform is going to be the same as the L2 norm of the Fourier transform of F, right? And so, so H preserves the L2 norm. Right? Is that okay? Okay. Because you see that if you take the Fourier transform of this guy and take its L2 norm, well, that's just going to be the L2 norm of the Fourier transform of the original function, right? Right. And then by Poincarel's theorem, we know that this is going to be, that's true. Right? So H is unitary. And another observation that we want. Third observation is if we look at the composition of H with H, what is it? What is it? What is it? You see? What does H do? Well, H you think of as you take the function, you take its Fourier transform, multiply the Fourier transform, and then flip it back. Right? So you take the Fourier transform again, right? Multiply that guy by multiply the Fourier transform by this again, right? So you're going to get -1, right? And you flip it back, and you just get -1 times your you just get a -1 here, right? So you get -1 times the function itself. Right? So you get H composed with H. It's just negative the identity operator. Is this clear? Is this clear? Maybe it's not. Spencer, is it clear? So okay, so just think of what the Hilbert transform does, right? The Hilbert transform says take your function and take its Fourier transform, and then multiply the Fourier transform by the sign and divide by I. Right? Multiply the Fourier transform by sign, and then take the inverse Fourier transform of that. Okay, take the inverse Fourier transform of that. So if you do the Hilbert transform again, it says take the Fourier transform of that thing, where you're going to come back to the thing with the sign and I applied to it, right? And then hit that thing with the sign. Well, that will cancel. That will cancel off. You have sine squared. That doesn't do anything, and you'll have 1 over I squared, right? That's say 1 over -1 or -1, right? So you have then your original function's Fourier transform times -1, right? And then you take the inverse Fourier transform of that. Well, that just gives you -1 times the original function, right? Right? So if you do the Hilbert transform twice, you just get negative your function. Okay. Okay. So the Hilbert transform, we're talking about it, thinking about it defined this way as a multiplier operator. But the main thing we're going to go for today is to show that the Hilbert transform is something called a singular integral. So actually, it's pretty interesting the way. So what's going to happen in the next section is that so what we're getting is that and we just saw that the Hilbert transform is bounded from L2 to L2. Right? It's unitary on L2. In the next section, we'll use complex analytic methods to get the Hilbert transform bounded on LP between 1 and infinity. Okay. But the really exciting thing that happened was that in the 60s, Stein and Berkman showed that it was possible to sort of circumvent any complex analytic methods and just use purely real analytical methods to get LP boundedness of not only the Hilbert transform but a whole class of operators called singular integral operators. So they used certain techniques to sort of avoid the constraint of having to use complex analytic methods. The trouble is that the methods that we're going to show in to get the LP boundedness don't work. They don't work in higher dimensions. They don't work in higher dimensions, and so creating a method that avoided the complex analytic methods allowed you to say we could do this in all dimensions. So that was sort of the exciting thing in 1964. And that was sort of the beginning of like the new boom in harmonic analysis. But Stein and his author here are showing how everything links together, right? How the Hilbert transform sits in the middle of these results of complex analysis, and will also sit in the middle of these real analytic results. So we'll do first the proof using complex analytic methods, and then we'll show you what happens when we introduce the real analysis. So this is it. Here is a statement that will seem to be mysterious to you. The Hilbert transform is a singular integral. So this is the main result for today, and I think we can do it in the last 20 minutes. So here's the proposition for F in L2. Let h sub e, h sub epsilon be the integral of f of x minus t 1 over t dt for t greater than or equal to epsilon, and we have 1 over some constant. Okay. Then h sub epsilon of f is in L2 for all epsilon greater than 0, and the Hilbert transform is actually the limit of these guys. So the limit of the h sub e's, so maybe I should just write it that way. The limit of the h sub epsilons as epsilon goes to 0, and I'll erase the x's, in the L2 sense. Okay. So, that is, these guys converge back to the Hilbert transform, that operator that we had before, which we define as a multiplier operator. These guys actually converge to the Hilbert transform in the L2 sense. Okay. So one writes that one often writes something like this, that this is the principal value of the integral f under ddt. Okay, that's basically just an abbreviation for what we're writing here. Okay. But what you want to think, you think that the Hilbert, what this does is that it recognizes the Hilbert transform as something like a convolution, right? As a convolution of f against the kernel 1 over t, right? So you're taking f and you're convolving it against this thing. Now that integral doesn't make any sense. That integral doesn't make any sense because you're integrating you've got this 1 over x, right? So, in what sense does it make sense? It's in this sense. So this is what's called a singular integral, convolution with a kernel that has singularity. Okay. And what Stein and Pfefferman did was to extend this to a whole class of kernels and figure out what exactly you needed for the kernels, what properties you needed of the kernels to make the LP condition hold, LP boundedness hold for the operators. Later on, people tried to do more advanced things where you had a kernel, but the kernel had singularities not just at a point, but along like some variety of points, along something with dimension 1, or something with higher dimension. That turned out to be very hard. Okay. Okay. So we're going to recognize the Hilbert transform as a singular integral. So let's first recall that these two formulas that we had earlier. We had the formula for the conjugate Poisson kernel. Okay. And we have the formula for the Hilbert transform. And so, if you look at the difference in LT norm, if you look at the LT norm of the difference, right, you get the LT norm of this thing. Because the L2 norm of the difference is by Plancherel's theorem, it's going to be the L2 norm of the Fourier transform of the difference, right? The Fourier transform of the difference is this thing, okay? Because I'm going to be with some constant of size 1. Is that okay? Right. This is by Plancherel's theorem. This is the same thing as this. Right. And the Fourier transform of the Hilbert transform is this. The Fourier transform of this thing is this. And then you subtract them and you get this thing. So what you notice is that the limit of phi convolved with q sub epsilon as epsilon goes to 0 is the Hilbert transform in the LT norm. Right? as y goes to 0, right? This goes to 0, and so what we have is we have the convolution with the conjugate Poisson kernel converges to the Hilbert transform in the L2 sense. Okay. So what we need to show is that that these guys get close to these guys in the L2 sense, right? And once we have that, then that'll do it, right? Because then these guys will converge to the Hilbert transform in the L2 sense. So let's look at it. Right? We need to show that the L2 norm it suffices to show that the L2 norm of this goes to 0. Right? As epsilon goes to 0. Okay. Everything all right? Okay. So let's look at it. Okay. So let's consider this thing. Well, by definition, this is whatever pi integral here f of x minus t t minus q epsilon. Okay, of course, by definition. And let's if we notate delta sub epsilon x as 1 over pi x minus q epsilon x, where x absolute value greater than epsilon, and just negative q epsilon x for x smaller than epsilon. Then the above can be written just as f convolved with delta epsilon x. Okay, so just introducing a notation for convenience. So this thing, using this delta notation, we're just going to abbreviate like this. So what we're hoping is that the L2 norm of this thing goes to 0. Okay. So let's make some observations. First, well, you remember what Q was, right? Q epsilon x is x over pi x squared plus epsilon squared, right? Which is odd, right? And certainly whatever x is odd, right? So these delta guys are odd, right? That is. The integral of the delta is 0. Right? They satisfy a cancellation. They satisfy a cancellation condition. The second thing to notice is that if we look at each of these guys, they can all be expressed as dilations of delta 1 this thing, x over x squared plus 1, which is smaller than 1 over pi, 1 over x squared plus 1 for x bigger than 1, we see that delta, all of the delta epsilons are all in L1. And they all, in fact, they all have the same L1 element. Okay, so so here we go. Let's finish it up. Let's consider f can fall with delta epsilon. Well, of course, that's just this. But we play a trick here. We slide in an fx. Those of you who were in the Fourier analysis course may remember we played this sort of trick before. Right? We're allowed to slide in, we're allowed to put in this constant because the integral is 0. Right? So we're just, right, we've added on this term, right? So this is 0. Right, because delta is an odd function. So here's where the cancellation is used, and in fact, we'll see very shortly that this sort of cancellation is crucial. We actually really need this cancellation for this to work out. So we slide in, we use the cancellation to slide in that term, and then let's do a change of variable and bring this back to delta 1. Okay. So let me show you what happens. If you using Cauchy's inequality, Cauchy's integral inequality, if we take the L2 norm of convolution, that is controlled by the L2 norm of the integral of the L2 norm of the integrand. Right. And we pull out. We pull out the delta 1 of t, since it doesn't depend on x. So, right, Cauchy's inequality says that when you're taking that the LP norm of an integral is bounded below by, it's like the triangle inequality for LP. So we use Cauchy's inequality here, and you see what happens, right? As epsilon goes to 0, right? the L2 norm of this is going to go to 0, right? And so, you know, we know that these guys are in L1, and so by dominated convergence, we get the integral of 0, which is 0. So by dominated convergence, we get that this thing's L2 norm goes to 0. And so, so those HEs converge to the F convolved with Q sub E's, which in turn converge to the Hilbert transform, Bn. So we get that the Hilbert transform can be realized as the L2 limit of these truncated integrals against a singular kernel. Truncated convolutions of the function against a singular kernel. And so the Hilbert transform is a singular integral. So that's what those 2 pages were about in the textbook. Or was it 3 pages? It was not more than 4 pages. But yeah, that's what was going on. Okay. I think now is a bad time to ask for questions, but I'm going to ask sort of belatedly. Do you have any questions? Was any part, I should have stopped sooner, but was anything opaque? Did anything seem opaque? Yeah.
Very close to the beginning,
Yeah.
you wrote down that when you take the Hilbert transform and subtract F convoluted with conjugate Poisson,
Yes.
that the L2 norm of that was equal to the L2 norm of this.
Yeah.
What was that about?
Okay, so that was just using Cauchy's theorem. So you know that this thing is given like this, e to the 2 pi c1 sin c e to the 2 pi c. And you know that the Hilbert transform is given like this, right? That is, the Hilbert transform is the inverse Fourier transform of this function. Okay, right. This is the inverse Fourier transform of this function. Okay. Similarly, that this convolution against the conjugate Poisson kernel is the inverse Fourier transform of this function. Okay, so now we're talking, we said what is the, what's the L2 norm? What's the L2 norm of the difference? Well, you know the L2 norm, by Poisson theorem, the L2 norm of the difference is the L2 norm, and the L2 norm of the function is the same as the L2 norm of the Fourier transform, right? So you say, okay, we're going to take the Fourier transform of these guys. But each of these guys is the inverse Fourier transform of something, right? So we're taking then the L2 norm of this thing, of this difference, right? So we get the L2 norm of minus that. And there's the sign constant where we take absolute values anyway, so that just vanishes. So you get the L2 norm of that. Okay, So it's just, it's Poincaré-Gauss theorem, that the L2 norm of something is the same as the L2 norm of its Fourier transform. That the Fourier transform is unitary on it. Okay, other questions? Okay, that's it. That's it. Oh, let me hand back some homeworks.